So I'm just going to go through some basic image processing and analysis for AFM images. The platform that I'm going to be working on is called MountainSPIP. If some of you may recall, SPIP or SPIP was an AFM image processing software created in the 90s. And then a few years ago, it merged with Mountains from Digital Surf, and now it's on this platform. It's been merged onto this platform called MountainSPIP. If you don't have it and you're interested in some of these features, I think there are 30-day free trials available from Digital Surf's website. So I have called up the first image that I want to work with. And just in terms of the jargon for MountainSPIP, they call raw data studiables. And then if we're going to do any calculations or manipulations of them, that will be through operators. So you'll see things like flattening and plane fitting that I'll talk about later, which are useful operators. And then we can also do some analyses or studies. So things like a 3D view and a histogram that we will cover also. But the first thing you want to do when you open up your image is you want to make sure that your Z-scale and your offset are set correctly. And so we have several ways to do that in MountainSPIP. If I just hover over my Z-scale, as you can see here, this little square shows me where the offset has been set, which by default right now it's in the middle of the image. I also see a histogram here in gray, so I can see where most of the data points are. So I could move that offset into the middle if I choose. That's probably a little bit better. And then that's on the right side of the Z-scale. And then on the left side of the Z-scale is associated to how I set the Z-scale. What color corresponds to what Z. So I can move this up and down in terms of what Z the dark values correspond to, what Z the bright values correspond to. So I can do this all manually. I can also go to enhancement and then optimize, have the software do it manually. Have the software automate it. Now if I go back to manual, I'm going to leave this optimized mode. I also have the ability, if I right click here, all these parameters are what's shown up here on the icons. They're just in a list, so maybe a little bit easier to see. I could hit access settings. I could impose a particular scale if I wanted. Let's say I wanted all my images to be on the exact same image scale, and that was 350 nanometers. So I can impose a 350 nanometer Z scale if I wanted. And so again, this optimization of the views is really important. So if I go to my amplitude channel, I can see that this visualization is pretty far from my ideal. So I'm going to need to play with that in terms of both the offset and how I adjust the coloring on that Z scale. So I can really highlight some of these images, some of these features and morphologies better. So that's obviously a lot better than what we started off with. So that was our height, that's our amplitude, this is our phase channel. And again, you know, that background is a little dark for my taste. So I might try and play around with it, again, this Z scale as well to see if I can get a little bit more visualization of what's happening on this background. But so again, playing around with the offset and your Z scale is the first step you want to do, and it's a very important step so that you can properly visualize all the different features in your surface. Another really important tool, I'm actually going to have the software optimize this. Another really important tool is cross-sectional profiles. We need cross-sectional profiles in order to measure lateral and vertical distances in our image. So I'm actually, let's see if I can, yeah, that's a little bit better. The optimization was a little bit too aggressive. So in order to do the cross-sectional profiles, I have to call up an operator. So I'm going to call up operator. extract profile. And this is the profile operator for MountainSPIP. MountainSPIP is in general a very powerful software, and it probably will have more features than you need. But they're all really illustrative and useful. So I encourage you to kind of learn them. So when I extract a profile here, I can either do a horizontal one or a vertical one, or I can pick, across whatever direction I want. Can do kind of a crazy profile. Let's say I wanted to include all the rubber domains, just measure along them. I can do that, or even a circular profile. But let's just stick with a kind of traditional horizontal profile. I can draw them simultaneously across all the channels. I don't think I'm going to want to do that. I'm just interested in the height channel here. And I can either I can average the profile across a certain length. So right now across a certain width. So right now I'm averaging over 100 nanometers. I can increase that as relevant. This would be 500 nanometers. That's kind of thick. Or I can just not average at all. So I'm going to hit OK. And now I've got the profile and I can move it and see if I can, let's say I wanted to measure some of these rubber domains. Yeah, so I'm capturing now 2 rubber domains here. Let's see if I can actually capture now four rubber domains. And let's say I want to now measure, make some measurements. So I would select my line profile. I would go to studies. I would hit distance measurement. And now I can position the cursors as I see fit to get both the horizontal and vertical distance between these cursors. I can pull up multiple sets of cursors here. Let's say I now have 3 sets of cursors. Let's say I want to measure the depths of a series of these rubber domains. So this is one set. This will be another set here. And so now I can quickly compare the depth of all of these rubber domains with multiple sets of cursors. And of course, you can export your results either as an image or as a table, whatever you need. So cross-sectional profiles are very useful. And then the final study that I want to discuss, which is also very useful, are histograms. So that's a study. We're going to go into histogram. And histograms are basically distribution of Z values present in the image. And they're a really quick way to see kind of what's going on in the image. The way it works in MountainSPIP, you get all the channels at once. And so I can just start clicking through for the histograms of, so my height, my amplitude, and then my phase. And what's very illustrative about this particular image is I know I have 2 components here. So if I look at the height image, I can tease out a little bit of that component of a peak that's representing these rubber domains of the lower heights, but it's pretty small relative to this big broad peak, which is most of the image. The amplitude, if I click here, not surprisingly, there's no difference. There isn't meant to be a difference, right? The amplitude is just the error channel. But then if I click on the phase, which is this channel here, I actually see the most clearly my 2 different channels, where this is the matrix here. This is my rubber, and I can even measure the difference between the 2. And so clearly the phase shows the best distinction of these 2 components out of the 3 channels that I was looking at in terms of the height and the amplitude. So I really encourage people to use histograms extensively throughout their visualization of AFM. It really helps the interpretation. You'll see in the flattening, we're going to use histograms for also masking purposes. So it's super useful to do. And then finally, the last capability I want to show is a thresholding parameter. Let's say you want to block a particular component out. You can threshold it out based on whatever channel you want. So for example, let's say I want to get rid of all the rubber domains. I want to look at only this matrix. I'm actually going to pick a different palette for what I'm masking out. So that's this guy here. So I'm going to threshold based on the histogram. And so now everything that is in blue is going to be masked out, not included in the analysis. And I'm going to hit OK. And so you can, let's go back to the phase because that's where we were applying it. These yellow now are my non-measured points. Let's turn them into pink so it's a little bit easier to visualize. And so now all these rubbers have actually been thresholded out. So if I drop a cross-sectional profile, which would be here, let's do it on my phase image, you can see that, oops, I actually want to do it just on phase. You can see that as I drop this cross-sectional profile, all these rubbers or peaks of the rubbers have been chopped off. They're no longer included. So now you have an image of just the polypropylene matrix, which you might want to do further analysis on. So these are kind of the basic visualization tools in terms of adjusting your Z-scale and offset, using cross-sections, histograms, and thresholding to really properly analyze your image. I just want to go over one more visualization tool before we jump into the image processing, and that is the 3D visualization that I think everyone kind of knows and loves. Just to quickly show on MountainSPIP, so if I want to do a 3D visualization, that's considered a study. So I'd go to study, then 3D view. And so you get your 3D view here of the topography. You can do a 3D view of any of these channels. But what I think is particularly useful that people should use is the ability to overlay or paint one channel onto the other so that you can look for correlations between the channels. So for example, here, I've got my topography, and the way you do overlay in MountainSPIP is pretty easy. They give you the topography and texture channel right there. So let's say I wanted to paint or overlay the phase onto the topography. Now what I see is that the coloring is coming from my phase image, but there's still the three-dimensional underlying topography as well. So you can clearly see that the phase, that bright white, is corresponding to the rubber domains. And we can see even these inclusions here. These are little inclusions. And there's not a direct topographic correlation with that because they're kind of independent of topography, but this also gives a fairly complete visualization of your data by being able to overlay one channel over the other. And as usual, you can right click and get a lot of different options in terms of whether you want to export it, export the image, and other various properties of it. You can also, you've got a lot of the options up here in terms of you can amplify. I was kind of doing that manually with the scrolling. We can add in axes. So full customization as usual. But the 3D with the overlay of one channel onto the other is really useful. So now I want to go to the most common image analysis, which is flattening and plane fitting. So I'm going to close this document and I'm going to open another studyable, which is a grid. And this, I'm just going to focus actually on, oops, let me open it one more time. I just wanted the actual document, the actual studyable that we will work on. So let me just open it one more time. And I'm going to delete all of this. Okay. So this is a grid image. I'm going to put it into a palette that we're more used to. I'm also going to put this into landscape mode, which is this way, so that we can make the screen, the images bigger. So this is a grid of rectangular pits and a flat background. I can see already the histogram here on the color scale has these two peaks. We just went over histograms, so I'm just going to pull it up here. That at least shows it vertically. Ideally, this image should have two delta functions as their peaks. And so while it does have two peaks, there's a lot of structure to them and they're really broad. And the reason for that is that this image needs some processing. It is not correctly set. And so there are two different kinds of processing we can do. We can do what's called these global plane fits, as well as line by line flattening. And the reason we need to process these images at all is due to the nonlinearities and artifacts associated with the hardware in the AFM, particularly the piezos in there. So that's why we need to adjust both on a global level with plane fitting and then on a line by line level to adjust for the artifacts associated with faster scanning. So we're going to start. So let's first start by dropping a cross-sectional profile, which we had just discussed. So I'm going to extract a profile and I'm going to do a custom one now where I want to do it along this background here just to see what's going on with the background. I don't need to average. I'm a single profile here is fine. And I can see there's quite a wavy background going on here, which should be flat. And the reason there is this wavy background is, again, this is due to global, there's global curvature that needs to be removed. So let's go ahead and remove that. And the way we do that, because we're going to actually modify the image, it's called an operator. So let's click on the image and call operator. And you can call up the plane fitting one of two ways. The quickest way is this leveling. But what the leveling does is it allows you to remove a first order plane fit only. So the way MountainSPIP works when you call an operator, it shows you the original surface and then the resulting surface. And so you can either let the software pick a least squares plane based on the image, or you can define the plane by 3 points, where you try and cover as much of the area as possible. And you say, okay, this is supposed to be this area is supposed to be a plane. But if I do that, I can see that I still have banding. I can see this kind of orange and white banding in the background, which is suggestive that a first order plane fit is simply insufficient for this image. So instead of calling up this leveling wizard here, I'm going to go to the more advanced version, which is a remove form, where now I can remove a high order plane from this image. And so right now it looks like if I select a second order plane fit, again, this is my original, this is the result, and it shows you what it's removing. You can see, again, I'm still left with this banding of this darker orange, bright yellow, dark orange here. And this actually shows you the kind of plane it removed, which is not exactly what our curvature was here. So then if I go to the third order plane fit, I can see the resulting surface now finally has a no banding. And the kind of surface that has been removed in terms of this bright, dark, that's exactly what that background banding looked like. So this third order plane fit, I think is how we're going to go. So we're going to hit OK. And we're going to scroll down. And let's just do another histogram now on this plane fit image. So I'm going to call up the study histogram. And let's move this guy here below. And let's make this. So now we can compare this histogram to the histogram above here. Much cleaner, much better. And then you can even measure the distance between these 2 points to see. That's a great average calculation on your entire grid here in terms of the difference between the pits of the matrix. So 106, let's see. That peak is probably around there. So it looks like it right now it's measuring 108 nanometers. However, there's still width to these peaks. And also, if I look closely at this image, I increase it a little bit, I see all these lines here. And those lines are a result of artifacts associated with the raster scanning of the image. So now we have to do a line-by-line flattening. This was a global fit to get rid of the curvature. Actually, let's drop a cross-sectional profile here. And we're going to drop it along the same area that we had. Let's see how it looks now. And you can see now this cross-sectional profile is much flatter than our original profile because we did remove this global curvature. But now, like I said, we still have this line-by-line problem associated with the raster scanning. So we need to remove that, and we do that by line flattening, which is an operator. Then we hit line by line. And again, the way MountainSPIP works, it shows you the original surface, and then it shows you the resulting surface. And so right now, we are subtracting a first order polynomial from each line. And it definitely cleaned it up, right? You can see this, all these big lines went away, but I still see some lines showing up here all over. So I think first order is not enough. I'm going to go to second order, better, but still, there's still some lines. And let's go to third order, see how that looks like. That looks much better. Probably going to keep it like this. You know, the general rule of thumb is you want to do the least amount of image processing as possible. So less is more here. So you want to be conservative. Now we're doing the line by line profile, but notice that these pits are actually gray. And the reason they're gray is they've been masked out. I'm actually going to change the mask color to a different palette so that we can see exactly what's being masked out. And so you need to mask out these features, because if you don't mask out, right now we're not masking out, you see all this banding here? What's happening is when the software is trying to fit each line to a particular form, it's including these pits. So you're going to have these artifacts now that have been induced by this line by line fitting. So we need to mask those out. This is probably one of the most common mistakes that I see in image processing is when people, when they're flattening, they do not mask out either very high or very low features, and then they induce even more artifacts in their image. So we are going to mask them out, and MountainSPIP has several ways to mask out. So first, it's called automatic structure exclusion. You have to select whether you are excluding pits or mountains or both. You can assign some leveling, which is a 0th order plane fit. Then you can also, so this is all automated. Then you can also assign, it finds the features and then does a little bit of a weak dilation. So adds a little bit more, or even a strong dilation. So there it added a little too much or none. What I prefer to do is I prefer to use a thresholding parameter here. So I can call up this threshold operator, and now I can pick exactly where my how I'm picking the masking based on the histogram of the image. So I want to include, basically, these are my pits, this is the background, and I want to include everything except that background. And I'm keeping an eye on an image here, on the image, to make sure that I don't go overboard, right? So if I go all the way up here, I'm going overboard. I'm catching this area here, and I think it's just too much of a border on those pits. So I'm going to back up a little bit. You know, this is an iterative process. I can look also at the resulting corrected surface, see how it's looking. And it's an iterative process. You know, something you want to play with and see what is best. I'll probably leave it here for now. So I can either use a histogram or their automated way to do so. So I've masked out these little pits. Now I have my corrected surface. I'm going to hit OK. And here's my resulting surface. And the best way to analyze it is our histogram. So let's do, I'm going to reduce this back. All right, so how does this histogram now compare? Let's pull it up and compare it with the histogram we just did on the plane fit data. Let's size it correctly. And you can see now my peaks are much sharper, much better. Huge improvement over the plane fit. The flattening really did a huge improvement. And if I can pick, I can probably make a more accurate measurement of the distance between these pits. So now 108. There was a 107.9 there as well, but here we have a better clarity and better definition. So actually we can use these histograms to see the progression of, this was our initial image, then we plane fit, and then we finally flattened, and really made a big improvement if we look at the image itself, right? This is what we started out with, and this is where we ended, a big improvement in the image. So flattening and plane fitting are ubiquitous for AFM analysis. Plane fitting, the larger the scan size, the more likely you are going to have to plane fit. And flattening, pretty much every image you're probably going to need to flatten to adjust for the raster scanning artifacts. Again, lower order is better, but these are really useful tools and ones that will be needed. And again, a reminder, if you do flatten, please do mask out your hills and valleys. And then just one final note, which is something unique to MountainSPIP. This whole workflow that I did here has been saved, which means that I can save this document and anyone else can step through it. It also means that I can recall operators and play with them. So for example, let's say I decided my plane fitting, yeah, maybe I didn't want third order. Maybe I wanted, I don't know, fifth order, which is way too aggressive. I can hit OK. And actually you can see there's even some banding that appeared. It was too much. But let's say I wanted to do fifth order, I can hit OK. And then it applies that operator. Now this fifth order and everything, this fifth order plane fitting, and then everything after it is just adjusted as follows. So I can go back and retweak any step in the process that I wanted in the workflow. Anyone can follow it now. You can save it. You don't need to screenshot, shoot it. And then if I have a lot of images that need the same kind of workflow, I can just right click here, substitute, and put in a different studyable. So that's kind of unique to MountainSPIP, but also something that I particularly enjoy in terms of this workflow for teaching and showing other people. But this concludes the image processing section of the master class. And again, we just went over some of the most common tools available for analysis, which was visualization, adjusting the Z-scale and offset, cross-sectional profiles, histograms, 3D analysis, and then the very important processing of plane fitting and line fitting. So with that, we'll be happy to take any questions. Thank you.